Alright everybody, I just wanted to do this derivation of this equation that we talked about in class today, the FIFE equation for RC circuits. Again, this equation works for charging or discharging. You just have to know the proper final and initial values. So I'm going to go ahead and derive it for us just so that we can know where it comes from, and then you're free to use it anytime you want. You don't obviously have to derive it. But let me draw like a little example circuit. Just put a voltage, some DC voltage source here. And let's call this R, C, and we'll call this source. Well, it doesn't really matter what we call this source. It's basically going to be the voltage here is going to be Vs. It's basically the voltage of the source. So I guess we could call this Vs, but again, this node voltage is going to be Vs. That's what I really care about. And then I'm sure everyone would agree that this voltage would be Vc, or basically my voltage across my capacitor. Okay, so let's get another color and let's label some currents here. Focus the camera. So let's call the current flowing through my cap, we can call that I2, and we'll call the current flowing through my resistor I1. Okay, so KCL, basically what KCL tells me that all the currents, the sum of all the currents leaving a node is equal to 0, right? So I1 plus I2 should give me 0 in this case. Basically, it's the same as saying, you know, minus I1 is equal to I2, and then if I add I1 over to the other side. So, but I could say minus I1 is equal to I2, and then if I add I1 to both sides, right, minus I1 plus I1 gives me 0, so I get 0 is equal to I2 plus I1. Okay, so that's just from KCL. But okay, so in that case, let's write an equation for I1. I could say that I1 is equal to basically Vc minus Vs divided by R. Okay, and I'm going to say that Vc minus Vs over R. Okay, that's just Ohm's law, right? The difference in voltage across the resistor over the resistance. And then I2 is my capacitor current, which we've seen before. It's going to be C dVc dt, right? It's the difference in capacitor voltage with respect to time multiplied by C. Okay? So if I take these two equations and I do KCL, I basically get V. Here, let me move my laptop a little. It's kind of in my way. I'm going to get Vc minus Vs over R plus C dVc dt equals 0. Right? That's my KCL for these two currents. Basically, I1 plus I2 is going to give me 0. Where this is I1 and this is I2. Okay, so now what I could do is I could subtract one of these terms over to the other side. Here, let me come down here and continue this. So basically, now that that's all set up, section it off, switch colors. Let's go with brown. Okay, so I can say Vc minus Vs over R is equal to minus C dVc dt. Okay, and now similarly to my previous derivation, what I'm going to do is I'm going to do what's called separation of variables to solve this differential equation. Okay, so I'm going to divide this side by a minus C, and I'm going to divide this side by a Vc minus Vs. So basically, if I divide minus C on both sides, here, basically, let me write it out. I'm multiplying by negative 1 over C on both sides. And that gets rid of the negative C. So what I end up with is basically Vc minus Vs over RC, and that whole thing is now negative. Basically -1 times all of that, and then my -1 over C and my -C cancel here, so I just get dVC dt over here. Now I'm going to divide this VC minus VS over, so I end up with just -1 over RC equals dVC dt times basically 1 over VC minus VS. So I took this and I basically divided it out of the other side. Okay, and now the last thing I'm going to do is a separation of variables, which means I need to move this dt over to the other side. So I get -1 over RC times dt is equal to 1 over VC minus VS dt. Okay, and now I'm ready to actually integrate this. Okay, so I'm going to integrate from 0 up to some time t, that's the time t where I would be interested in the capacitor voltage. And I'm going to integrate my capacitor voltage. Okay, sorry, this side's not dt, this is dVC. Okay, so dVC stays on the right and dt comes over to the left. Okay, and I'm integrating my capacitor voltage basically from some initial capacitor voltage, okay, to some current capacitor voltage that I'm interested in at time t, right? At time 0, my capacitor voltage is my VCI. At time t, my capacitor voltage is some new capacitor voltage, VC, okay? So now let's just come up here and kind of continue this. If I integrate the left side, -1 over RC is just a constant, so what I end up with is basically -1 over RC times t minus 0, which is just -t over RC, and that's equal to, and again, if we remember right, the integral of 1 over x is basically the natural log of x. So if I treat VC minus VX or VS as my x, then my integral here is the natural log. Also, we have to absolute value it because of the way that natural logs work. I get VC minus VS integrated from, oh sorry, I keep writing 0, it's VCI up to VC. Okay, VC being the capacitor voltage I'm interested in at time t, and VCI being my initial. So I can write this as -t over RC is equal to the natural log of basically VC minus VS minus the natural log of VCI minus VS. Okay, and now because of log rules, basically log rules tell me that ln of A minus ln of B is equal to ln of A over B, so I can write this as a fraction. -t over RC is equal to the natural log of basically VC minus VS over VCI minus VS. Okay. And now I can exponentiate both sides to get this ln to go away, which gives me e to the -t over RC, or I guess it could be, we could rewrite it as tau now if we wanted to. And now the natural log is gone, we can drop the absolute value sign. VC minus VS over VCI minus VS. And what we're trying to do now is solve for VC, because that's what we're curious about is our capacitor voltage at some time t. Okay, so what I'm going to do is I'm going to multiply this over to the other side, and then I'm going to add VS. Okay, so first I multiply this over to the other side, that gives me VCI minus VS times e to the -t over RC, and I said I'm going to add VS, so let's add VS, and then that's equal to VC. And now this is a loose form of my capacitor voltage equation, my FIFE equation. Basically, let's take a look back at the circuit. If I have some capacitor voltage C and or VC, and we're talking about this circuit, right? We already know that basically if I'm discharging this capacitor or I'm charging this capacitor, let's say that it's charged to 5 volts and I set VS equal to 0. Well, eventually, all this current is going to flow through this resistor, and the capacitor will discharge to 0. Well, let's say my capacitor is initially 0 and my Vs is 5. Well, I know that my current is going to flow this way and charge my capacitor until my capacitor is equal to 5. So I could say that my Vs, my source voltage, is going to be my capacitor's final voltage. In either case, whatever that source voltage is, once no current is flowing, my capacitor voltage is going to be equal to my Vs. So I'm going to call Vs my capacitor's final voltage. And now I'm going to rewrite this equation. And I'm going to flip it around so that I can say Vc, my capacitor voltage, at some time t is equal to Vs, but I'm going to rewrite Vs as my capacitor's final voltage, Vcf, plus my capacitor's initial voltage minus the final voltage times e to the minus t over tau, basically, where tau is equal to RC, right? And there is my FIFE equation. So that's where my FIFE equation comes from. It just comes from a simple KCL, and then the solution is basically based on this solving of this simple differential equation. And again, this works in any case. Remember that for the typical charging equation, when we charge from 0 to some value, we basically set VCF as our final value, and VCI is 0 because we're starting at a discharged value, and we get basically our charging equation that we've seen already, which will be VCF times 1 minus e to the minus t over tau. And if we're discharging, we set VCI equal to whatever our capacitor is charged to, and VCF equal to 0, and those VCFs go to 0, and we get our discharging equation. So yeah, I just wanted to give this to you all so that you had something to go off of, so you know where this equation comes from and you can see how it's derived. If anybody has any questions, please feel free to ask. And I hope everybody has a great rest of the night, a good Tuesday, and I'll see you all in class on Wednesday.